This is the Chapter 6 pre-class lecture, Measuring Energy Changes and Calorimetry. So calorimetry is a technique that's used to measure the amount of energy that is released during a combustion reaction. And to do so, a device called a calorimeter is used. And then you can calculate what's called the heat of combustion. That is related to the amount of heat given off when a specified amount of a substance burns in oxygen. Heats of combustion are reported in units of energy per mole or energy per gram. And so some common units would be joules per mole or joules per gram. Also, kilojoules per mole or kilojoules per gram. And so calorimeters will have a certain amount of water in them. And then the initial temperature of the water is measured. And then the substance that the fuel or the food or whatever that you're trying to measure the heat of combustion for, that substance is burned or combusted. And when that substance burns or is combusted, that heat that's released as a result of the combustion is transferred to the water, and the water heats up. And then you measure the final temperature of the water after all of your fuel or food or whatever sample that you're burning, after it has burnt completely. After it has burnt completely, you measure the final temperature of the water. And then you calculate what's called the change in temperature. Which is called the delta T. Delta T is equal to the final temperature minus the initial temperature. And then you can calculate the amount of heat that is absorbed by the water. So the substance, whether it's fuel or food that is being combusted, is going to lose heat. And heat is usually symbolized with a lowercase q. So the heat is going to be lost by the substance being burnt or combusted. Heat is going to be gained by the water. The same amount of heat that is lost by the substance being combusted is going to be equal to the amount of heat gained by the water. And so to calculate the heat that is gained by the water, it's going to be equal to the mass of the water times what's called the specific heat of water, symbolized with a C, times the delta T for the water. Water has a specific heat of 4.184 joules per gram degree Celsius. So burning of a fuel or anything else that is combusted is an exothermic reaction because heat energy is being released by the reaction. Methane is a fuel, and when you combust methane, 802.3 kilojoules per mole of energy is released, which is equivalent to 50.1 kilojoules per gram. And so with methane, CH4, being combusted in the presence of oxygen, looking at the reactant side of the combustion reaction, for every 1 mole of CH4 that gets combusted, 2 moles of oxygen are also combusted. So there are 2 moles of oxygen are needed to combust every 1 mole of methane. And then your products are CO2 and water. For every 1 mole of CO2 that gets produced, 2 moles of water get produced. So here is an energy level diagram. Here you have the energy of the reactants. Down here is the energy of the products. The energy difference is your delta H of combustion. This is your heat of combustion. Delta H is a term in thermodynamics known as enthalpy. And so delta H with the subscript COMB is the change in enthalpy of combustion, or you can call it simply heat of combustion. And so this delta H, our reactants, those chemical bonds in those reactants have to be broken. And those atoms have to be free to rearrange to form our 2 products, CO2 and water. So this delta H of combustion for methane is equal to the energy that's needed to be absorbed to break the bonds in the reactants. Plus the energy released to form the bonds in the products. And so whether it's a combustion reaction or any other type of reaction, the delta H, so if it's not a combustion reaction, you just say delta H. But if it is a combustion reaction, you can just say delta H, or you can say delta H of combustion. So this is the energy profile diagram for methane. Here are some energy profile diagrams for other fuels. So you can see that the energy difference, which we call the delta H of combustion, or the heat of combustion, for each type of fuel is different. Wood having the smallest energy difference, methane having the largest. What that means is that methane gives off more energy per gram than octane, which gives off more than coal, which gives off more than ethanol, and wood gives off the smallest amount of energy when it is combusted. And so we said that for exothermic reactions, it's when energy is released. So combustion reactions are exothermic. Endothermic reactions are those that absorb energy. And so the net energy change is positive for endothermic reactions. For endothermic reactions, the net energy change is negative. And so looking at question 1, burning charcoal, that's a combustion reaction. So it is exothermic. When water evaporates from your skin, water evaporating means you start off with liquid water and you end up with the water evaporating, so therefore it vaporizes and turns into a gas. And so in order for liquid water to turn to a gas of water, energy or heat has to be absorbed. And therefore this is endothermic. Glucose is synthesized inside of the leaves of a plant. This is photosynthesis. And therefore, the plant takes in CO2 and water vapor and uses the energy from the sunlight as a catalyst, absorbs that sunlight to produce glucose and oxygen. So sunlight being absorbed, this is also an endothermic reaction. And then ice melting means you're taking ice, solid water, and converting it into liquid water. So to do this, heat or energy, heat energy has to be absorbed. In order to melt something, you've got to add heat. I apologize. I'm having a little allergy problems and I'm feeling a little flu symptoms because I had my second dose of my vaccine this morning, so I'm feeling a little cold flu symptoms. And so this is also endothermic. So question 2, how much heat in kilojoules is released from the combustion of 1,525 grams of gasoline that has an octane rating of 91. So the octane rating of 91, this means that 91% of the gasoline is octane. And so how much heat in kilojoules we need to solve for Q, which is the mass of the octane, times the delta H of combustion of the octane. So therefore, the amount of heat, Q, is going to be equal to 1,525 grams times 0.91. I take my 91%, I convert it to a decimal. All of this 1,525 grams is not octane. Only 91% of it is. So we first need to multiply 1,525 times 0.91, and that'll give us the grams of octane. And then we need to multiply that by the delta H of combustion for octane. The delta H of combustion for octane is negative 44.4 kilojoules per gram. The grams cancel. We do our math, and we get a Q of negative 6.16 times 10 to the fourth kilojoules. That's how much heat is released. And because it's exothermic, that's why you see the negative sign. That means heat is released. If the Q was positive, that means that the reaction's endothermic and heat is not being released, but absorbed. But for combustion reactions, they're always exothermic, and the amount of heat is going to always give you a negative value, because that means that the delta H is negative because the reaction's exothermic, and that's telling you how much heat is released. And that brings us to the end of discussing calorimetry and the amount of heat released during a reaction.